Most people, when they imagine other worlds, picture two doors. Door 1, the cosmos is teeming with company, and we just have not run into anyone yet. Door 2, the cosmos is empty, and we are alone here, and that is just how it is. Those are the two answers people argue about in books, on podcasts, in the comments under every space documentary ever made. There is a third door. It is the one we are walking through tonight. It is the possibility that the universe is not empty at all. It is the possibility that it is full of worlds where the conditions for life arrived and then left. Worlds where life may have started and then stopped. Worlds with the porch light still on and nobody home. 6,087 confirmed worlds outside our solar system. Hundreds of billions estimated. Tens of billions in habitable zones. The receivers are on. The signal level is essentially zero. And the strangest thing about that silence is that the math says it should not be silent at all. Get comfortable. Hit subscribe if you are new here, because by the end of this, you are going to understand that the sky is not a question about who is out there, but about who used to be. Now, let's slowly ease into this. Part 1. The Tube on Mars. There is a rock sitting on Mars right now, and the people who put it there will probably be retired by the time anyone gets to hold it. The rock is sealed inside a small titanium tube about the size of a piece of chalk. The tube has a number stamped on the side, and a cap that was screwed shut by a robot in July of 2024. The robot's name is Perseverance. The rock came out of a sedimentary mudstone that the team named Cheyava Falls, a slab of layered Martian sediment on the floor of an ancient river channel inside Jezero crater. The sample inside the tube has its own name. It is called Sapphire Canyon, and it is the most important rock in the history of astrobiology, sitting alone on the surface of another planet, waiting for the species that drilled it to come back. The reason this rock matters is the pattern in it. When the rover's onboard instruments looked at the sediment Sapphire Canyon was cut from, they saw small dark nodules scattered through the mudstone. Some of them were the size of poppy seeds. Some of them were larger, with darker cores ringed by lighter halos, and the science team started calling those ones leopard spots. The chemistry of those nodules turned out to be a specific combination of three things. There was iron phosphate in a mineral form called vivianite. There was iron sulfide in a mineral form called greigite. And there was organic carbon in the mudstone matrix around them. If you found that exact combination on Earth in fine-grained sediment with that exact morphology in a place that used to be the bottom of a freshwater lake, you would not hesitate. You would call it a microbial biosignature. Iron and sulfur chemistry of that kind, in those patterns with those halos, is the chemical fingerprint of microbes that pull energy out of sediment by shuttling electrons between iron and sulfur compounds. We have lake beds on Earth, billions of years old, where that exact assemblage tells the story of a microbial mat that lived and died in the mud. The patterns Perseverance, found in Cheyava Falls, are the patterns that on Earth would be a textbook case. The paper describing the find was published in the journal Nature in September of 2025, after more than a year of internal review at NASA and external peer review by scientists who were not on the rover team. The authors are careful people. The phrase they use, the one that took a year to settle on, is potential biosignature. They list the alternative explanations. The patterns could in principle be produced by certain water-rock reactions that do not involve life at all. They could in principle be produced by certain low-temperature volcanic processes. They could in principle be produced by chemistry that ran in a sterile mudstone billions of years ago, without anything alive ever being involved. The paper does not say that any of those alternatives are more likely. It says that they have not been ruled out, and that ruling them out requires laboratory work that no rover can do from another planet. So the tube sits there. It sits on the surface of Mars in a cache the rover deposited for a future mission to come and pick up. That future mission, the Mars Sample Return Mission, was originally designed to retrieve the cache and bring it home to Earth in the early 2030s. The original architecture was reviewed in 2024 by an independent panel that concluded the program was running far over budget and would need to be re-engineered. The return date has slipped. The current best estimates put sample on Earth somewhere in the late 2030s at the earliest, with some scenarios stretching into the 2040s, which means the rock sits there, the wind blows across it, the Martian sun rises and sets on it. The temperature swings 60 degrees Celsius between noon and midnight, and the tube does not move. The most consequential rock in the history of our species, the one that might contain the only piece of evidence we will ever physically hold from a second origin of life, is sitting on the surface of another planet for at least another decade, and there is nothing we can do about it. We can look at the photographs. We can read the analysis from the instruments the rover carries with it. We can argue about what the patterns mean. We cannot pick it up. Tonight, we are going to sit with that rock, and we are going to sit with the larger question it opens. Because Mars is not the only dead world we know about. It might not even be a rare one. The universe, as far as we can currently see it, contains a confirmed inventory of just over 6,000 worlds outside our solar system, and a credible estimate of several hundred billion more in this galaxy alone. The natural assumption is that some fraction of those should be alive, someone should be home. But the more we learn about what it actually takes to keep a world habitable, the more it starts to look like the real story is not about life starting. The real story is about life lasting. By the time we are done tonight, you are going to see the night sky a little differently, not as a place that is empty, not as a place that is teeming with company we just have not run into yet, but as a place that might be very, very full of something quieter than either of those answers, something that already happened, something that ended. We are going to spend a little time with that tube on Mars first, because it is the closest physical thing we have to the question. Then we are going to walk across the solar system to the other dead planet, the one nobody likes to talk about, the one we usually skip past in school. We are going to look at the kind of star most planets in this galaxy actually orbit, and we are going to ask what habitable zone really means around a star like that. We are going to spend some time with the largest extinction in the history of life on Earth, the one nobody talks about, because it was caused by the air you are breathing right now. We are going to think about what the night sky actually is, which is a postal system where every letter arrived together but was sent at wildly different times. And then we were going to sit at the end, with the open window we are inside of tonight. Get comfortable. The rock is not going anywhere, neither are we. Here is where most people get the universe wrong, when they think about whether anyone else is out there. They imagine two doors. Door 1, the cosmos is teeming with company, and we just have not run into them yet. Door 2, the cosmos is empty, and we are alone here, and that is just how it is. Those are the two answers people usually argue about. There is a third door, and that is the one we are walking through tonight. It is the possibility that the universe is not empty at all. It is the possibility that it is full of worlds where the conditions for life arrived, and then left. Worlds where life may have started and then stopped. Worlds with the porch lights still on and nobody home. The number to sit with first is 6,087. That is the count of confirmed worlds is outside our solar system as of January of 2026, listed in the NASA Exoplanet Archive, which is the official register where confirmed planetary discoveries get logged. NASA publicly crossed the 6,000 milestone in September of 2025, and the count keeps climbing. To put that in scale, there are about 195 sovereign countries on Earth. We have more confirmed worlds beyond our own solar system than we have countries on our own, by a factor of more than 30. And those are just the worlds we have actually managed to detect. The real number, the estimated number, is much larger than that. There are roughly 200 billion stars in the Milky Way, give or take a factor of 2, depending on which census you trust. The working assumption based on data from the Kepler and TESS Space Telescope missions is that nearly every star has at least one planet, and many stars have multiple planets. So when astronomers do the arithmetic, they end up with somewhere in the hundreds of billions of planets in this galaxy alone. Of those, the latest estimates put the number of planets sitting inside the formal habitable zone, the region around a star where liquid water could theoretically exist, on the surface, somewhere in the tens of billions. That is a lot of worlds, so why is it so quiet? The first thing to understand is that habitable zone is a misleading term, and it might be the single most overused phrase in popular astronomy. It only means that liquid water could exist on the surface of a planet at that orbital distance, in principle, under some assumed conditions. It does not mean water is there. It does not mean water was ever there. It does not mean the planet has an atmosphere capable of holding water. It does not mean the surface temperature is currently within liquid water's range. It does not mean the surface is anything like a surface a person could stand on. It just means the orbit sits at roughly the right distance from the star for liquid water to be thermodynamically possible. So when you hear that there might be tens of billions of habitable zone planets in this galaxy, what is actually being said is that there are tens of billions of orbital slots now where liquid water on the surface is not immediately ruled out by distance alone. The conditions could still be ruled out by 1,000 other things, and very often are. Out of the 6,000 confirmed exoplanets we have, most of them are nothing like Earth. The first ones we found were hot Jupiters, gas giants so close to their stars that their cloud tops glow. They were the easiest to detect, which is why we found them first. Then came super-Earths, rocky worlds bigger than ours, often in orbits so tight that a year there lasts a few Earth days. Then came tidally locked planets, where one side faces the star forever and the other side faces away forever, leaving a permanent sunlit hemisphere baked into rock and a permanent dark hemisphere cold enough that the air itself could fall as snow. Then came planets in scorched orbits with no atmosphere left at all. Planets with surface gravity high enough that a human heart could not pump blood against it. Planets where everything that mattered about the surface had already happened billions of years before we knew the planet existed. When you look at the catalogue of what we have actually found, the planets that resemble Earth in any meaningful way are rare. Out of 6,000 confirmed worlds, the number that could be described as roughly Earth-sized, in roughly the right orbit, around a roughly stable star, is in the low dozens. Not the low thousands, not the hundreds, the low dozens. So, part of the silence is just that most of the worlds we have detected were never going to talk to us in the first place. They could not. They do not have the chemistry, the temperature, the air, the time. They are stones in space, and we have been counting them carefully, because counting is what we know how to do, but that is only part of it. Because the truly strange thing is not the worlds that never could have been alive. The strange thing is the worlds that maybe could have been, the Earth-like candidates. Those are out there in real numbers, even by the most conservative estimates. And out of those, we have no signal, No radio call, no optical flash, no chemical fingerprint we can confidently identify as life. Nothing. That is the silence that is hard to explain. The silence of the worlds that should, by any decent statistical argument, have something on them. There is an image that keeps coming back when you sit with this. The universe, at least the part we can see, is not quiet because nobody ever existed in it. It is quiet the way an old library is quiet. You walk in at night and the lights are off, but the building is still there. The shelves still there. The books are still there. Every spine you pull off has a real author behind it. Real ink, real pages. The library was not built empty. Somebody filled it, but it has been a long time. The writers are gone. The readers are gone. The lamps overhead have burned out, one by one. The building has gone quiet. The books are still there. The voices are not. That is the third door. The library is real. The shelves are full. The lights are off. When astronomers map a planet through the Kepler mission, or its successor TESS, what they actually see is a star that dims a little, every few days or weeks, in a regular pattern. The dim is the planet crossing in front of the star, blocking a small fraction of its light. That is it. That is all we see for most of them. We never see the planet directly. We see a slight repeating shadow, and from that shadow we work out how big the planet is, how close to its star it sits, how long its year lasts, and a few other rough properties. We do not see what is there, so we see that something is there, and then we go to the next star. That is what most of exoplanet science looks like. You stand outside the library. You can tell from the shape of the shadows on the wall that the building has shelves and aisles and corners. You can guess at the number of books. You can guess at their size, but you cannot go in. And what you mostly cannot do is tell from the outside whether anyone ever read them. The other thing to understand about the silence is the timing. Even if every Earth-like world out there had developed intelligent life at some point in its history, the odds of any two civilizations existing in the same moment inside a galaxy whose history spans more than 10 billion years are slim. Human radio communication has been a thing for about 130 years. Recognizable human civilization goes back maybe 10,000. Anatomically modern humans, around 300,000. The Earth has been habitable for about 4 billion. If you compress all of Earth's habitable history into a single calendar year, the entire span of human existence shows up in the last 90 seconds before midnight on December 31st. Modern science fits in the last second. Now picture a galaxy in which every habitable world has its own version of that calendar, started at a different time, ended at a different time, with most of the calendar quiet and ordinary and only a few seconds in each year where anything loud is happening. The chance of two of those calendars overlapping in those few loud seconds is small. Most of the time, you would reach into the universe at random, and you would pick a world that either had not started its civilization yet, or had finished it, or had never had one at all. Silence is not proof of empty, it is proof of timing. There is a phrase astronomers sometimes use, half joking, when they are talking about all of this. They call it the Great Quiet. Not the Great Filter, which is a specific argument about what stops civilizations from growing. The Great Quiet is just observation. It is just the listening. The fact that the receiver is on, and the signal level is essentially zero, and has been essentially zero for as long as we have been able to check. Some of that quiet might be that nobody is out there. Some of it is almost certainly that somebody was, and is not anymore. The library, in other words, is real. The shelves are full, the lights are off. Whether anyone is still inside is a question we do not have a tool sharp enough to answer yet. What we do have is the shape of the building, and a sense, growing every year, of how many rooms it contains. If you want to know what one of those quiet rooms in the library looks like up close, we do not have to travel far. We already have one. It is the planet next door. Part 2. Mars, the twin next door. Mars is the easiest dead world to talk about because we can see it. You can step outside on the right night, look up, find the small sea steady reddish light, and there it is, the fourth planet from the Sun, the next door neighbour, the one you do not have to imagine because it is actually there, in the same sky you stood under as a child. For most of human history, Mars was a wandering light and the name of a god of war. It became a place sometime in the late 1800s, when telescopes got good enough to show that the reddish dot was a world with polar caps that grew and shrank with the seasons, a world with dark patches that some astronomers convinced themselves were vegetation. By the late 1800s, the Italian astronomer Schiaparelli was reporting straight lines across the Martian surface, which the American astronomer Percival Lowell convinced himself were canals dug by a dying civilization to move the last of their water from the poles to the equator. None of that turned out to be true. The lines were an artifact of the human eye, trying to make sense of fuzzy images at the edge of resolution. The dark patches were dust and stone, not forests. There were no canals. But the idea of Mars as a dying world turned out to be closer to right than anyone in 1890 realized. And the picture we have built up since then is grim. The Mars we have today is, by any reasonable definition, dead. The surface temperature averages about minus 63 degrees Celsius. That is roughly the coldest temperature ever recorded on the Antarctic ice sheet. Except that on Mars that is the average, not the extreme. The atmosphere is so thin that liquid water on the surface would boil and freeze almost in the same instant, because the pressure is too low to keep water in its liquid state. Standing on the surface of Mars today, with a perfect spacesuit, you would still feel the cold soak into the soles of your boots within minutes. The sky overhead would be a pale butterscotch colour, not blue, because there is not enough air to scatter light the way Earth's atmosphere does. The sun, when you found it in the sky, would look smaller and dimmer. The horizon would feel close, because Mars is a smaller world and the curve of the ground falls away faster. It would feel like a place that something used to live in. That feeling, it turns out, is not just a feeling. Here is what we know. Mars used to have a magnetic field, a real one. A planet-wide one, generated by a molten metal core spinning at the centre of the world, the same way Earth's core spins now. That magnetic field acted as a shield. It deflected the solar wind, which is the constant stream of charged particles the sun throws off in every direction. The shield meant that whatever atmosphere Mars had, it could hold on to. The shield meant water on the surface could stay water, because the air pressure was high enough to keep it liquid. The shield meant a sky thick enough to feel like a sky. Then the shield went down. The current best estimate from paleomagnetic analysis of Martian meteorites that landed on Earth and from orbital magnetic surveys of the Martian crust is that the global magnetic field of Mars collapsed roughly 3.9 billion years ago. That date has been pushed and pulled by different studies in the past few years. A high-profile paper out of Harvard, published in 2023 and reaffirmed by follow-up work through 2025, suggested the field may have lasted slightly longer than the older textbook estimate, but the headline is the same. The core cooled, the dynamo stopped, the shield went away. After that, the atmosphere started to bleed, not in one event. Over hundreds of millions of years, the solar wind picked at the top of the Martian atmosphere, knocking the lighter molecules off into space, one at a time, in a process so gradual that if you had been standing on the surface watching, you would not have noticed anything different from one century to the next. But the budget was negative. More air was leaving than was being replaced by volcanic outgassing. Eventually the bank account ran out. NASA's MAVEN spacecraft, which has been measuring this process into real time since 2014, gives a current loss rate of about 1 to 2 kilograms of atmosphere per second escaping into space. That sounds small. 2 kilograms per second is nothing on a human scale. Spread that rate over 4 billion years, and it adds up to most of what used to be there. Today, the surface pressure on Mars is somewhere between 0.6 of a kilopascal and 1.1 kilopascals, depending on altitude and season. Earth's surface pressure is 101 kilopascals, so Mars currently has less than 1% of the air pressure we have here. To find air that thin on Earth, you would have to climb to about 30 kilometers above the surface, which is about 3 times higher than a passenger jet flies. That is the kind of air Mars now has at ground level, but there was a window, and inside that window, things happened. The Curiosity rover, which landed in Gale Crater in 2012, has spent more than a decade slowly driving up the slopes of a mountain in the middle of that crater, examining the rocks layer by layer. Gale Crater used to be a lake. We know that now with the certainty that comes from chemical and stratigraphic evidence accumulated over more than 4,000 sols of observation. The layered mudstones, the river-worn pebbles, the calcium sulfate veins, the clay minerals that only form in standing water, the carbonates, the iron hydroxides. All of it tells the same story. Around 3.8 billion years ago, this part of Mars was full of liquid water. There was a deep lake, fed by rivers that drained the surrounding highlands. The lake stayed for a long time. The mineral evidence suggests it persisted, on and off, for something like 700 million years, with the last clearly habitable conditions winking out somewhere around 3.1 billion years ago. 700 million years is a length of time that is hard to hold in your head. Life on Earth in any complex form anyone could recognize has only existed for about 600 million years. The Cambrian explosion, when animals with hard parts first showed up in the fossil record, was about 540 million years ago, which is to say, the Martian habitable window on the surface lasted longer than the entire history of complex animal life on Earth so far. And on Earth, in the same era, life had already gotten started. The earliest convincing evidence of microbial life on this planet shows up in rocks, around 3.5 billion years old. There are hints, debated but real, of biological signatures going back to 3.8 or 3.9 billion years, which means that the two planets were running the same experiment at the same time. They had liquid water at the same time. They had atmospheres at the same time. One of them, we know for sure, started growing life. The other one had every ingredient to do the same thing. And then, somewhere around 3 billion years ago, the conditions on Mars stopped being friendly. Which brings us back to the rock. The Perseverance rover landed in Jezero Crater in February of 2021. Jezero, like Gale, used to be a lake. You can see in the satellite imagery the fossilized remains of an ancient river delta, where water flowed in from the surrounding highlands and dropped its sediment in fan-shaped layers. Perseverance was sent to Jezero specifically because of that delta, because river deltas on Earth are where biology tends to leave the cleanest record. River deltas concentrate fine sediment. Fine sediment preserves chemical signatures. If anything ever lived in that water, the best place to find traces of it is in the layered mud that piled up at the river's mouth billions of years ago, before the lake dried up. Perseverance has been driving across that delta, taking samples since it arrived. The rover carries a coring drill and a cache of titanium tubes. Each sample drilled out of a rock gets sealed in its own tube, given a name, and recorded for retrieval by a future mission. The hope, when the mission was designed, was that the samples would be brought back to Earth in the early 2030s where laboratory instruments far more sensitive than anything a rover can carry could analyze them for biology. In July of 2024, Perseverance drilled into a rock the team named Cheyava Falls. The drill produced a small cylindrical sample, the size of a piece of chalk, which the team named Sapphire Canyon. The team noticed something unusual right away. The rock contained small nodules, dark-colored, distributed through the sediment, in patterns that on Earth would be unusual outside of a biological context. Some of them looked like poppy seeds. Some of them looked like leopard spots, with darker cores and lighter halos around them. Chemical analysis with the rover's onboard instruments identified the nodules as concentrations of iron phosphate in a mineral form called vivianite, together with iron sulfide in a mineral form called greigite. On Earth, that combination, in those patterns, in that kind of mudstone, is what gets produced by certain microbes when they do their chemistry. Specifically, when iron-breathing and sulfur-breathing bacteria pull energy out of sediment by shuttling electrons between iron compounds and sulfur compounds. The patterns Perseverance saw in the rock it sampled are the kind of patterns that a textbook on Earth would call a microbial biosignature. The paper describing the find was published in Nature in September of 2025, after more than a year of careful internal and external review. The authors, who have spent their professional lives looking at exactly these kinds of features in Earth rocks, are extremely careful with their language. The phrase they use is potential biosignature. They list the alternative explanations. The patterns could be produced by chemistry that is not biology, by certain volcanic processes, by water-rock interactions that do not involve life at all. They do not claim they found life on Mars. They claim they found something that on Earth would be the first thing you would point to as evidence of life, and that other explanations remain on the table. The sample is sitting on the surface of Mars right now in its sealed tube. The Mars Sample Return Mission, which would bring it home for analysis in laboratories that can do tests no rover can, is in flux. The original schedule, which would have had the tube back on Earth in the early 2030s, is now under significant architectural and budgetary review. The current best estimate for retrieval is somewhere in the late 2030s, possibly later, which means that the most consequential rock sample in the history of our species is going to sit on the surface of another planet for at least another decade, waiting for us to come get it. In the meantime, all we have is the photograph. There is an old idea about photographs, that they are not so much images of people as they are of moments. The person you photograph today will keep aging. The moment frozen on the film does not. So you end up holding in your hand a small rectangle that is a piece of time, separated from the person it came from. That is what Cheyava Falls is, a piece of time. Maybe a piece of Martian time when something was alive. Maybe a piece of Martian time when nothing was. And the rocks just happened to assemble themselves into patterns that look like life would have made them. We do not know yet. The image is real. What it shows is still being worked out. If you have ever moved into a house someone else used to live in, and you have gone up into the attic, you know the feeling. There is a box up there. The box has photos in it. Real photos, real people, real faces in clothes you do not recognize, in rooms you do not recognize, in places you have never been. You are holding pictures of people who walked through your hallway and ate in your kitchen generations before you bought the property. They are not your family. They are just people. The fact that they were there, doing ordinary things in the same physical space you now live in, is hard to absorb the first time you really notice it. Mars is like that attic. You climb up there expecting dust, expecting nothing, and instead you find a photo album. The pictures are real. They are of someone you have never met. And the camera that took them stopped working a very long time ago. That is the situation we are in with Mars. The rock in the tube is the latest photograph from the attic. There may be others. There almost certainly are. The Perseverance mission is one of dozens of robotic and orbital missions that have been studying this planet for 60 years. We have been knocking on the door for 60 years. Sometimes the door rattles. Sometimes a window opens. Mostly the house is quiet. The wind blows red dust against the porch. Mars's porch light is still awesome, in the sense that the sun still shines on Mars every day. We have been ringing the doorbell for 60 years. Nobody answers. Mars is the obvious dead world, the one we usually talk about. But it is not the only one in our neighbourhood. The one we usually skip past is on the other side of us. The one we file under hot rock and stop thinking about. The one whose death is harder to think about, because it died differently. Part 3. The twin we don't talk about. We don't think about Venus the way we think about Mars. Mars gets all the cultural attention. Mars is the rover planet, the future colony planet, the one people put on the covers of magazines next to a square-jawed person in a spacesuit. Venus is the one we mostly skip. You learn about Venus in school for about a week. It is the one with the runaway greenhouse. It is the one that is too hot. The greenhouse gone wrong example. The lesson where the teacher tells you that this is what happens if a planet gets too much carbon dioxide, and then you move on. That telling is wrong, or at least it is missing the most important part. Venus on paper is Earth, almost exactly Earth. It has roughly the same diameter as our planet, about 6,051 kilometers, compared to Earth's 6,371. It has about 81% of Earth's mass. It has roughly the same bulk density, which means the same general mix of rock and iron in its interior. It formed at roughly the same time, out of the same protoplanetary disk, from the same mix of materials. It sits inside the inner solar system. It is our sister world by every standard astronomers, used to mean by the term sister world. If you grabbed a stranger and showed them the basic specifications of two planets, one labelled Earth and one labelled Venus, and asked them which one supports life, they would have no way to tell. And here is the part I genuinely think people should sit with for a minute. Venus may have been habitable with liquid water oceans on the surface for as long as 2 to 3 billion years. That is not a wild speculation. That is the conclusion of climate models run by NASA's Goddard Institute for Space Studies. The Way and Del Genio simulations, published originally in 2016 and refined in subsequent papers through 2020 and beyond, take what we know about Venus's likely early conditions, run a three-dimensional climate model forward in time, and find that under reasonable assumptions about cloud cover, atmospheric composition, and a slowly rotating planet, Venus could have had a stable temperate climate with surface oceans for somewhere between 2 and 3 billion years before it tipped into the state it is in now. 2 to 3 billion years. To put that in scale, life on Earth has been around in any complex form, anything more than single cells, for about 600 million years. Venus, on this timeline, had liquid surface oceans for longer than complex multicellular life has existed on Earth, 5 times as long, give or take. There was on the surface of that planet an environment that under any reasonable definition would have been habitable, for an amount of time that dwarfs the entire existence of any animal anyone has ever named. Whether anything used that habitat is another question entirely. We have no fossils from Venus. We have at this point no surface samples from Venus. The few Soviet landers that touched down on the Venusian surface in the 1970s and early 1980s lasted, on average, less than 2 hours before the heat and pressure killed them. The longest survivor, Venera 13, made it just over 2 hours. The pictures it sent back show a flat, tan landscape of broken rock under a heavy, sulphurous yellow sky. No animals, no plants, definitely no civilizations. But the question is not whether anything is there now. The question is whether anything was there 2 billion years ago, when the planet might have looked completely different. Then, somewhere around 700 million years ago, the conditions on Venus changed. The triggering event is debated. The leading candidates include a massive global resurfacing event, where the entire surface of Venus was repaved by volcanic activity in a relatively short geological window, possibly within 50 to 100 million years. There is also the steady brightening of the Sun, which has been increasing in luminosity by roughly 10% every billion years over its main sequence life. There is the possibility of a runaway volcanic outgassing episode that pumped enormous amounts of carbon dioxide into the atmosphere over a relatively short time. There is the possibility that more than one of these things happened together and crossed a threshold the climate system could no longer balance. Whatever the trigger was, the climate flipped. Water vapor, which is itself a powerful greenhouse gas, trapped more heat in the atmosphere. The hotter atmosphere held more water vapor. The more water vapor in the atmosphere, the more heat got trapped. The oceans began to evaporate. The hotter the atmosphere got, the more the oceans evaporated. The more the oceans evaporated, the more water vapor entered the atmosphere. The more water vapor entered the atmosphere, the hotter the atmosphere got. That feedback loop is what scientists mean by a runaway greenhouse. By the time the runaway finished, Venus's oceans were entirely gone. The water vapor in the upper atmosphere got broken apart by solar ultraviolet radiation. The hydrogen, being light, drifted off into space. The oxygen, being heavier, mostly bonded with surface materials and got locked into rocks. The carbon dioxide, which had been dissolved in the oceans and locked up in carbonate rocks, was now free in the atmosphere. And the atmosphere just kept thickening. Today the surface temperature on Venus averages about 464 degrees Celsius. That is about 864 degrees Fahrenheit. Hot enough to melt lead. Hot enough that you do not need to imagine standing on it. You do not get to stand on it. You would be dead in less than a second. The surface pressure on Venus is about 92 times Earth's atmospheric pressure. That is the pressure you would feel at the bottom of about 900 meters of ocean. Not 9 meters, 900. To find a place on Earth with pressure that crushing, you would have to go deeper than any human submarine has ever taken people. The Soviet landers that survived for those few hours did so because they were essentially deep-sea pressure vessels, built with hulls thick enough to handle the weight of an ocean's worth of atmosphere pressing down on them. The sky overhead, if you could somehow see it, is a thick yellow gloom full of clouds made of sulfuric acid. The clouds rain, but the rain never reaches the surface. It evaporates back into the atmosphere on the way down, because the lower atmosphere is so hot that liquid sulfuric acid cannot stay liquid in it. So the sky has weather, and the weather has acid, and the acid never lands. This is what Venus is now. A place where lead would puddle on the ground. A place where the air weighs 92 times what our air weighs. And that air is poisonous and corrosive and full of acid rain that never reaches the surface. A place that is, by any reasonable definition, hell. The way I keep coming back to this is something everyone has done at one point or another. You put a pot of water on the stove. You turn the burner on. You walk away, planning to come back when it boils. But you get distracted. You take a phone call. You answer the door. You forget about the pot. When you remember, you walk back into the kitchen and the bottom of the pot is glowing and the water is gone. That is Venus. For a long time the pot was fine. The water simmered. You could still see the surface of the water. You could still see the bottom of the pot. You could still cook in it. Then, slowly, the water level dropped. Then the pot was dry. Then the pot was glowing. Venus has been a glowing pot for 700 million years, and the burner will not turn off. Here is the part that, for me, makes Venus the harder world to think about than Mars. The oceans do not completely vanish. They leave a trace. If you look at the chemical composition of Venus's atmosphere with a sensitive enough instrument, and you measure the ratio of two kinds of hydrogen in the upper atmosphere, you find something that does not make sense unless Venus used to have a lot more water than it does now. There is regular hydrogen, the kind with one proton in the nucleus. And there is deuterium, the heavier kind with a proton and a neutron. Deuterium is rare. On Earth, it makes up about 1 part in 6,400 of the hydrogen in our oceans. On Venus, the ratio of deuterium to regular hydrogen is roughly 150 times what it is on Earth. That is not a small number. That is the kind of number that has only one good explanation. Light hydrogen escapes into space more easily than heavy hydrogen, because lighter things move faster at any given temperature. And the lightest things in the upper atmosphere are the ones that get knocked off into space by solar wind and ultraviolet light. So if you start with a planet that has both kinds of hydrogen mixed in its oceans, and you boil those oceans into the upper atmosphere, and you let solar radiation work on that water vapor for a few billion years, the regular hydrogen gets stripped away faster and the deuterium hangs around. Over time, the ratio of heavy to light hydrogen in the remaining atmosphere goes up. So when you measure Venus's atmosphere today, and you find 150 times Earth's deuterium ratio, what you are measuring is the chemical fingerprint of an ocean's worth of water that boiled into space billions of years ago, with the lighter component carried off first, leaving the heavier component behind in the air. The water is gone. The trace of the water is not gone. There is a kind of grief that comes with the detail when you sit with it for a minute. We do not usually think of planets as having ghosts, but Venus has one. It is chemical. It is measurable. It is there. The ocean that used to be on Venus is, in a real sense, still hanging in the air, just as a ratio of isotopes, just as a number on a spectrometer, the shape of an absence. We could detect that ratio from Earth, with the right telescope, 60 light years away. If a Venus-like world existed in orbit around another star, and we had the right instruments pointed at it, we could measure the deuterium signature in its atmosphere, and we could say, with high confidence, that this planet used to have a lot of water, and now does not. We could say it without ever going there. We could say it without ever sending a lander. We could read the obituary from a distance. There may be planets out there right now that we have already done that with. We may not have realized what we were looking at. The hardware to measure this kind of thing reliably across light years is just now coming online. With the James Webb Space Telescope and a generation of ground-based extremely large telescopes coming in the late 2020s and 2030s. The first time we read a Venus-like ghost on an exoplanet, we will not be making a discovery. We will be confirming something the universe has been recording on its own. The fingerprint of a former ocean, Venus's porch light, is still on. The light has been on for 4 billion years. The house burned down inside. So now we have 2 dead worlds in our own neighborhood. Mars, killed by a cooling core and a vanished atmosphere. Venus, killed by a runaway greenhouse and an ocean's worth of water boiled into space. Different deaths, same result. 2 planets, the same age, the same materials, the same construction, the same starting conditions. One of them in the dust, one of them in the fire, Earth in between. Which raises a question that ought to make anyone uncomfortable. How stable is any habitable window, anywhere? If 2 of the 3 rocky planets that start inside the Sun's habitable zone have already lost their habitability, by completely different mechanisms. What does that tell us about the third one? That is where we have to look next. Because as it turns out, the habitable zone itself is not a place you can plant a flag in and stay forever. It moves, and the planets it slides over change with it. Part 4. The habitable zone is a moving target. When people first hear about the habitable zone, the image that gets planted in their head is a kind of permanent neighborhood. You imagine a ring around a star. Inside the ring, it is just right. Outside the ring, it is not. The planets inside the ring are the good ones. The planets outside the ring are too hot or too cold. Earth is inside the ring, and that is why we get to exist. And that is basically the end of the story. Almost none of that is right. The habitable zone is real. The math behind it is real. It is very specifically the range of orbital distances from a star at which liquid water could, in principle, exist on the surface of a planet, given some basic assumptions about atmosphere and reflectivity. For our Sun, the habitable zone today is, in the most commonly used estimates, the orbital region between about 95% of Earth's distance from the Sun and about 170% of it, give or take. Different models give slightly different boundaries, depending on what assumptions they make about clouds and atmospheric composition. But the habitable zone moves. It moves because stars change. Stars are not steady. They look steady to us because human lifespans are short and stars change slowly. Over billions of years, we star brightens, cools, expands, contracts at different stages, and eventually dies. The brightening part is the part that matters here. A main sequence star, the kind our Sun is, the kind most stars in the galaxy are at any given moment, gets gradually brighter as it ages. Hydrogen in its core fuses into helium. The core becomes slightly denser. The pressure goes up. The temperature goes up. The fusion rate goes up. The star puts out more energy. Year by year, the increase is invisible. Over billions of years, it adds up. The Sun has brightened by roughly 30% since the Earth formed. That is not a minor adjustment. That is the difference between a comfortable indoor temperature and a fever. If the Sun today were as faint as it was when Earth was new, the planet would be a frozen ball. There is a paradox built into that fact called the faint young sun paradox, which is a fancy way of pointing out that the Sun used to put out a lot less light. And yet there is clear geological evidence of liquid water on Earth's surface, as far back as 4 billion years ago. Somehow, the early Earth was warm enough for water, despite getting much less sunlight than we get now. The answer probably involves a much thicker greenhouse atmosphere then, with much higher levels of carbon dioxide and methane keeping heat trapped on a much fainter Sun. But the relevant point here is just the brightening. The Sun has gotten about 30% stronger over 4.5 billion years, and it is still getting stronger. The current rate of brightening is roughly 1% per 110 million years, which sounds slow. Most things sound slow at that timescale. But the consequence of that brightening, applied to Earth's climate, is not slow at all. As the Sun gets brighter, the habitable zone moves outward. The orbital distance at which water can exist, as a liquid, pushes further from the star. The inner edge of the habitable zone, the line beyond which water would boil away under any reasonable atmospheric conditions, creeps outward year by year. Today, Earth sits comfortably inside the habitable zone. The inner edge is somewhere closer to the Sun than we are. In about 1 billion years, give or take a few hundred million, depending on which model you use, the inner edge will reach Earth's orbit. That is not the end of life on Earth. The mechanics are more complicated than that. As the Sun brightens, the Earth's surface warms. The warmer surface causes more water to evaporate into the upper atmosphere. The water vapor in the upper atmosphere gets broken apart by ultraviolet light. The hydrogen escapes into space, the same kind of process that played out on Venus. The oceans start to lose water. The chemistry of the surface starts to change. The kind of life that requires complex multicellular bodies and stable temperatures and oxygen and liquid water altogether starts to run out of places to live. Most credible models converge on a window of somewhere between 1 and 1.5 billion years from now before complex life on Earth becomes untenable. Microbes might hang on longer. Microbes can do a lot. There are places on the current Earth where microbial life is going about its business at temperatures well above the boiling point of pure water, inside thermal vents on the ocean floor, in conditions that would kill almost everything else we know. Some of that life might survive for a while, past the death of multicellular ecosystems. But the kind of planet we live on, the planet with forests and oceans and animals and rain and snow and seasons, that planet has roughly 1 billion good years left. If you push the timeline further, the situation gets worse. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin its red giant phase. The outer layers will swell outward. The Sun will get larger, much larger, hundreds of times its current diameter. The increased surface area will mean that even though the Sun's surface temperature will actually drop a little during this phase, the total energy output will go up by a factor of about 1,000. The orbits of the inner planets will be inside the expanding solar atmosphere. Mercury will be inside the Sun. Venus will be inside the Sun. Earth, by the most recent modelling done in the last few years, will most likely also be inside the Sun, somewhere around 7.5 billion years from now. Some scenarios let the Earth narrowly survive at the very edge of the red giant's atmosphere, scorched but not consumed. The central estimate is that the Earth gets eaten, so the planet itself has a kind of expiration date, and the habitability of the planet has a different, earlier expiration date. The way to think about the habitable zone is that it is not a place. It is a moment. There is something I learned to play years ago that helped me understand the habitable zone better than any diagram or article ever did. I learned a little piano, just enough to make the easy songs sound right. One of the first things you learn when you are learning piano is that the keys you can play with one hand are limited. You have an octave, 8 white keys, 5 black keys, all sitting within reach of your fingers when your hand is on the keyboard. If you want to play notes outside that octave, you have to move your hand. The habitable zone is the playable octave for liquid water. Within that range, you can do music. The notes work. Water exists in the form that supports life. Outside the octave, the notes are too high or too low, either too hot or too cold. The music falls apart, but the piano is not stationary. Someone is slowly pushing it across the room. Or, if you prefer the actual physics, the playable octave is sliding outward over time. The keys you used to be able to reach keep falling off the edge of the bench. Mars's keys fell off the bench around 3.5 billion years ago. Venus's keys fell off the bench around 700 million years ago. Earth's keys are sitting roughly in the middle of the playable octave right now. The piano keeps moving, the keys keep sliding. There are other planets we have found in other systems that may already be past their playable octave. There are planets sitting in what we currently classify as the habitable zone of stars that have been around for many billions of years and have done their share of brightening and may have already shoved their habitable zone past those planets. We see them and we mark them down in the catalogue, and we say liquid water could exist there. The truth is more complicated. Liquid waters could exist there if the conditions are exactly right at the moment we are looking. The conditions a billion years ago might have been very different. The conditions 1 billion years from now will definitely be different. We are seeing a snapshot. The snapshot does not tell us how long the conditions have been that way, or how long they will continue. Habitable zone, in other words, has a built-in time problem that we usually ignore when we talk about it. A planet is in the habitable zone now. That does not mean it always was. That does not mean it always will be. That does not mean it ever supported life at any point in its history. The phrase carries a sense of permanence that the physics does not actually justify. There is a related point that is worth lingering on. The habitable zone is calculated, in most models, assuming a planet has an atmosphere similar to Earth's. It assumes the planet has a magnetic field. It assumes the planet has stable rotation. It assumes the planet has water to begin with. None of those are guaranteed. Plenty of planets in the habitable zone have none of them. Plenty of planets that are not in the habitable zone today might have had all of them in their past. The phrase habitable zone is shorthand for a much more complicated reality, and the shorthand can mislead. What is true is that the playable range exists for any given star at any given time. What is also true is that the playable range slides over time, and the planets it slides over are different at different epochs in a star's life. A planet that is a perfect candidate for life now might be a frozen wasteland 1 billion years from now, when the star has dimmed by the right amount to push the habitable zone closer in. A planet that is a frozen wasteland now might become habitable 1 billion years from now, as the star brightens enough to thaw it out. The galaxy is full of planets in the wrong place at the wrong time. That is the part that is hard to swallow. There are likely planets out there right now that had their best era 1 billion years ago and missed everything they could have been. There are likely planets out there that have not started their best era yet and will not reach it for another 1 billion years. The number of planets that happen to be in their habitable era right now, at this moment, is a small fraction of the total. We are one of them. The window is open here. The window is closed elsewhere. And that is just our star. A calm, well-behaved yellow dwarf, putting out energy at a steady rate with relatively few outbursts, lasting a long time. The sun is, by stellar standards, an easy neighbour. Most of the stars in the galaxy are not like the sun. Most of the stars in the galaxy are smaller, redder, and significantly less patient with their planets. Most of the planets we have found, the ones in the so-called habitable zone, orbit stars that are not like our sun. They orbit stars that on a good day are merely violent. On a bad day, they are worse than that. And every day on those stars, from a certain angle, looks like a bad day. That is where we have to look next. Because most of the lottery tickets we have, in the search for life, are not the kind of ticket that pays out in the way we usually imagine. Part 5. Most stars are not like the sun. When most people picture a star with planets around it, they picture our sun, a yellowish, steady, even-tempered star hanging there at the center of the system, throwing off a comfortable amount of light, doing its job without making any fuss. That is what stars are supposed to look like in the cultural image. That is the kind of star you imagine when you imagine alien sunlight on an alien beach. That is not what most stars look like. Roughly 3 out of every 4 stars in the Milky Way are something called an M-dwarf, also called a red dwarf. These are small stars, much smaller than the Sun. They range from about half the Sun's mass down to about 8% of it. They are cooler than the Sun, with surface temperatures somewhere between 2400 and 3700 Kelvin, compared to the Sun's roughly 5800. Because they are cooler, they put out most of their light in the infrared, with the visible component leaning toward red, which is where the name comes from. They are dim, they are small. They are the kind of star that, if you replace the Sun with one, would leave the inner solar system in a permanent twilight. They are also, by a large margin, the most common kind of star in the universe. 3 out of every 4 stars you could ever visit in this galaxy are red dwarfs. 3 out of every 4 habitable zones being studied right now are around red dwarfs. 3 out of every 4 exoplanet announcements that include the phrase Earth-sized planet in the habitable zone are referring to planets that orbit red dwarfs. So when we talk about how many habitable worlds might be out there, we are mostly talking about red dwarfs by default. The math just works out that way, and that matters, because red dwarfs are not gentle. Here is the part that takes a while to absorb. Smaller stars like red dwarfs have a few features that look like they should be friendly to life. They have very long lifespans because they burn their fuel slowly. The smallest red dwarfs are expected to last for trillions of years, far longer than the entire current age of the universe. They put out steady amounts of energy over those long lifespans in the long run. Their habitable zones are small and tight, which means a planet orbiting at the right distance to receive Earth-like amounts of energy from a red dwarf is sitting very close to the star, much closer than Mercury is to the Sun. The orbital periods of these planets are short. A year on a red dwarf habitable zone planet might last anywhere from a few days to a few weeks. The planets are easier to find because they pass in front of their host stars, often enough that we get many opportunities to observe each transit. The signal is stronger because the planet blocks a larger fraction of the star's light. All of that is the good news. The bad news is that red dwarfs are magnetically furious. Smaller stars in general are more magnetically active than larger stars, especially when they are young. They produce more spots on their surfaces. They produce more flares. Red dwarfs have flares that can be, in some cases, 10,000 times more powerful than the most powerful solar flare our Sun has ever been recorded to produce. A flare that on the Sun would briefly knock out radio communications across half the Earth would, on a red dwarf, deliver radiation across the entire inner star system in concentrations that no biology we know would survive without serious shielding. And these flares are not rare events on red dwarfs, they are routine. The TRAPPIST-1 system is the place where this story gets specific. TRAPPIST-1 is 40.7 light years away from Earth, in the direction of the constellation Aquarius. It is one of the most extensively studied red dwarf systems we have. It contains 7 Earth-sized planets, orbiting in tight, compact rings around the central star, all of them closer to TRAPPIST-1 than Mercury is to the Sun. Several of those planets, labelled E, F, and G, sit in the conventional habitable zone of the host star, the orbital distances where surface liquid water would be possible if the conditions were right. On paper, it looks exactly like the kind of place we would want to look for life. 7 rocky planets, more than one of which could in principle support liquid water, around a single nearby star. Astronomers, and journalists were excited about the system when it was announced in 2017. They are still excited about it. It is one of the headline systems in exoplanet science, and almost everything we have learned about Memsa dwarf habitable zones in detail has come from observing it. In 2025, the James Webb Space Telescope measured TRAPPIST-1's flare activity over a sustained period and found that the star produces roughly 6 flares per day. 6 flares per day, every day. That works out to over 2,000 flares per year, every year, for billions of years. The planets sitting in the habitable zone of that star, which orbit closer to it than Mercury orbits the Sun, are taking those flares full in the face, without any of the buffer space that comes from being far from your star. They are right next to the speaker. The volume is at maximum. The volume has been at maximum since the system formed. The volume will be at maximum for the rest of the star's life, which is to say, for trillions of years. What does that do to a planet? Laboratory studies have tried to simulate it. They have taken cultures of various Earth microbes, including the most radiation-tolerant ones we know about, like a bacterium called Deinococcus radiodurans, which can survive levels of radiation that would kill any other organism instantly. They have exposed them to simulated red dwarf flare radiation, at the doses the TRAPPIST-1 planets would actually receive. The conclusions vary by study. The general picture, though, is that flares of this magnitude, repeated at this frequency, are enough to sterilize all but the hardiest microbes from any unprotected surface. Anything sitting in shallow water, in topsoil, in exposed environments, gets cooked. Some life might survive deep underground in caves in subsurface oceans below ice. But the kinds of habitable surface conditions that complex life on Earth depends on, the open sky, the running water, the photosynthesizing plants, are very hard to maintain on a planet that is getting hit with that kind of radiation every few hours, forever. There is another problem with red dwarf habitable zones, and that is tidal locking. Because the habitable zone around a red dwarf is so close to the star, the gravitational interactions between the star and any habitable zoned planet are strong enough, over geologically short timescales, to lock the planet's rotation to its orbit. The same face always points at the star. The other face never sees the star. One hemisphere is in permanent day, baking under a red sun that never moves in the sky. The other hemisphere is in permanent night, cold enough that even atmospheric gases might condense and snow out on the surface. The boundary between the two hemispheres, the terminator, is a narrow strip of perpetual twilight where the day side meets the night side. That terminator is the only zone where the temperatures might be reasonable for surface water. It is a thin ring of habitability on a planet that is otherwise either too hot or too cold to support an ecosystem. There are models that suggest a thick atmosphere with the right circulation patterns could redistribute heat from the day side to the night side, evening out the temperatures and making more of the planet livable. There are other models that suggest the atmosphere on the day side might just slowly evaporate and migrate to the night side and freeze out there, leaving you with a planet that has a frozen ocean of nitrogen and oxygen on one hemisphere, and no atmosphere at all on the other. Which model is right depends on details we mostly do not yet know about specific planets. The honest answer is that tidally locked habitable zone planets might be habitable in some cases on the strip with the right atmosphere, with the right luck. Or they might just be split planets, half oven, half meat locker, with a narrow band in between where nothing has the time to settle in. And then there is the more recent piece of bad news. The James Webb Space Telescope has now spent enough time observing the innermost planets of TRAPPIST-1 to make a confident statement about whether they have atmospheres at all. The verdict for TRAPPIST-1b at least is that it does not, or if it has one, it is so thin as to be undetectable. The radiation environment over the system's lifetime appears to have stripped whatever atmosphere the inner planets started with, leaving them as bare rocks. The outer planets in the system have not yet been ruled out in the same way, but the pattern is not encouraging. So when we count habitable zone planets in the catalogues and we end up at numbers like tens of billions across the galaxy, we have to be honest about what that number means. Most of those planets orbit red dwarfs. Most of them are sitting closer to their star than Mercury is to ours. Most of them are getting hit with flares many orders of magnitude more powerful than any flare our sun produces, several times a day, for the entire life of the star. Many of them are tidally locked. Many of them have already lost whatever atmospheres they once had. The phrase habitable zone, as applied to these worlds, is doing some heavy lifting that it does not really earn. I keep coming back to this image when I think about it, and I think it captures the situation as honestly as I can. A red dwarf habitable zone is like trying to live inside a boxing ring while an opponent 4 times your size throws a haymaker at you every 4 hours for your entire life, for billions of years. You might still be standing. You might even be conscious. There might still be a body in the ring at the end of the round. But the word habitable is doing some heavy lifting in that sentence, because the person who is standing has spent a lifetime taking blows that would have flattened most of the population by the 3rd round. That is most of the lottery tickets we have. 3 out of every 4. Most of the candidates for life that we are currently studying are sitting inside a fight that never ends. There are exceptions. There are red dwarfs that are quieter than the average, especially older ones, where the magnetic activity has settled down over billions of years. There are habitable zone planets around K dwarfs, the slightly more sun, like cousins of red dwarfs, which are calmer and longer lived than full M dwarfs, but smaller and dimmer than the sun. There are habitable zone planets around G dwarfs, the kind of star our sun is, but those are less common, harder to find, and not where most of the existing observations are pointing. The science community would love more of them. The catalogue has only a handful so far. The porch light is still on around TRAPPIST-1. It flickers 6 times a day. The bulbs are unstable. The wiring keeps tripping. Every time you think you are about to see the house, the porch goes dark again, and then the surge comes back, and the light flares so brightly that for a moment you cannot see anything else. That is what most of the lottery looks like. So now we have a sense of the scale. We have a sense of what most of the candidates actually are. We have 2 dead worlds in our own neighbourhood, killed by completely different mechanisms. And we have 3 out of every 4 habitable zone candidates orbiting stars that throw radiation at them every 4 hours for the entire life of the system. The math is starting to come together. The silence is starting to look less like a mystery and more like a consequence. But there is something else we have not talked about yet. We have been talking about how worlds die. We have not talked about what it means that the worlds we are seeing might not even be where we think they are in time. Because the sky we are looking at is not the sky as it is now. The sky we are looking at is a record. And once you understand what that record actually is, the silence starts to look different again. That is where we have to look next, at the night sky as a piece of mail. Part 6. The Library and the Mailbox. When you walk outside at night in a dark enough place to actually see the stars, what you are seeing is not the sky. You are seeing a record. Every point of light you can pick out with the naked eye, or with binoculars, or with a telescope, is light that has been travelling at the speed of light for some amount of time before it hit your eye. The sun you see is 8 minutes and 20 seconds old. The moon you see is a little over a second old. The brightest star in the night sky, Sirius, is about 8.6 light years away, which means the light hitting your eye left Sirius 8.6 years ago. The next time you see Sirius, you are seeing what it was doing, give or take, around the time of an event in your life from almost a decade back. Whatever Sirius is actually doing right now, at this instant, will not reach Earth for another 8.6 years. Light is fast. Astronomically, light is slow. Proxima Centauri, the nearest star to the Sun, is 4.25 light years away. The light you see from Proxima left in 2021 or 2022, depending on exactly when you are watching. The North Star, Polaris, is roughly 430 light years away, give or take some uncertainty in the measurement. The light you see from Polaris tonight left it before the American Revolution, before the United States existed as a country, when most of what we now think of as modern science had not been invented yet. The brightest visible stars are mostly within a few hundred light years. The faintest naked eye stars stretch out to several thousand. Some of the stars you can see with binoculars are tens of thousands of light years away. The light from the center of the Milky Way, which you can see as a faint smudge on a dark night when the conditions are good, left the galactic center about 26,000 years ago. The light from the Andromeda Galaxy, the only other major galaxy you can usually see without a telescope, has been traveling for about 2.5 million years. The light from the Andromeda Galaxy that is hitting your eye tonight left when our ancestors had not invented agriculture yet, had not invented language as we would recognize it, had not really invented anything. Andromeda's light is older than humanity. Then there are the galaxies the James Webb Space Telescope has been finding at the edge of the observable universe. The most distant galaxy JOST has imaged sent their light out when the universe was less than 5% of its current age. That light has been traveling for more than 13 billion years to reach us. The galaxy that sent it has changed in ways we cannot measure. It might still exist in some form. It might not. Whatever shape it is in now, we have no way of seeing the current version. We can only see the version from 13 billion years ago. So when you look up at the skies, you are in a real sense looking at history. The fact that this is technically true is something everyone has heard at some point in school. The fact of what it means to actually live in a universe like this is harder to absorb because what it means is that the night sky is a postal system. Each point of light is a letter. The letters were mailed at different times. They arrived at your eye all together at this moment, but they were not sent at the same time. Some were sent yesterday. Some were sent 1,000 years ago. Some were sent during the Roman Empire. Some were sent before any of our ancestors stood upright. A few of them were sent by senders who, by the time the letter arrived, no longer exist. That last one is the part that takes a minute. Stars die, not often in human terms, but constantly in galactic terms. There are stars in the night sky that, somewhere in the past few centuries or millennia, have ended. They have run out of fuel, collapsed, blown off their atmospheres, become white dwarfs or neutron stars or black holes. The transition can be slow, in the case of a small star fading into a stellar remnant, or fast in the case of a supernova. Either way, the star you see now is not the star that is there now. The star you see now is a memory. The light is still travelling, will be travelling for years or centuries or millennia after the star itself is gone. There is, somewhere in the visible sky, at least one star whose light is on its way to your eye right now, even though the star it came from no longer exists in any form we would recognize. You cannot tell which star. You cannot tell from the envelope. The letter looks the same as the letters from senders, who are still very much alive. You only know that some of them are from senders who are not. The sky we see is in a real sense a memorial. I want to push that thought further, because it connects to everything we have been talking about tonight. Every habitable planet we have detected, or might detect in the coming decades, is also a letter from the past. The light from a planet around a star 50 light years away is 50 years old by the time it reaches us. That means the atmospheric composition we measure is 50 years out of date. A planet around a star 100 light years away, 100 years out of date. A planet around a star 1,000 light years away, 1,000 years out of date. That does not sound like much for a planet. Atmospheric composition tends to change slowly. A few hundred years here or there, on a world that has been around for billions of years, should not matter much, and mostly it does not. But when we get to the edge of what we can plausibly detect, or when we start asking whether any specific planet is currently inhabited, the time lag matters. The light from a planet 10,000 light years away tells us what its atmosphere looked like 10,000 years ago. Civilizations rise and fall in less than that. If there was a technological civilization on a planet 10,000 light years away, and that civilization existed for, say, 5,000 years and then collapsed, and the collapse happened 9,000 years before the light we are seeing left them, then we might be looking at the light from a still active civilization. If their civilization had collapsed 11,000 years ago, we would be looking at light from after they were gone, and we would see signature of them at all. Whether anyone is out there right now is a question we cannot directly answer. We can only ask whether anyone was out there at the moment when the light left them. We cannot ask about now. The concept of now, applied to a star system thousands of light years away, does not have meaning in a way we can investigate. Now is a local concept. The universe does not really have a global now. So when we look up at the sky and try to figure out who is or is not out there, we are, in a real sense, opening a mailbox full of letters of different ages, from different senders, with no return address dates we can fully trust. Some of the letters are from people who are still home. Some are from people who have moved. Some are from people who died long before the letter arrived. We sort through them. We do our best. We make our maps. The maps are useful. The maps are also fundamentally maps of a place that may or may not still exist in the form the map describes. This connects to the harder thing, the thing we have been circling around all night. The universe might not be empty. It might be a graveyard. Many of the lights you can see could be coming from places where life happened, and then ended long before that light started its journey toward you. The deaths could have happened so long ago that the news has not reached us yet. The news is on the way. The news is 50 light years out, or 100, or 1,000, travelling at the only speed information can travel through this universe. We will get the news. We will not know when. We will see a star, and we will measure its planet, and we will find a signature that looks like life. The signature will be a fingerprint from a planet that may not have had life for a very long time by the moment we are measuring, and we will not be able to tell. The honest version of stargazing, the one that takes the physics seriously, is that we are reading mail. Some of the mail is recent, some of it is old, some of the senders are still home, some are not. The mailbox is enormous. The letters never stop arriving. You can spend a lifetime sorting through them. You will never finish. There is a particular feeling that comes with this, late at night, when you let it really sink in. You step outside, you look up, you find a bright star, you let your eye rest on it for a minute. You think about the years that light has been travelling. You think about what was happening on Earth when that light started its journey. You think about what was happening on the planet that sent it, if there was a planet, if there were any inhabitants, what they might have been doing on the day that particular photon left them on its long trip across the dark. And then you realize that the photon is just one photon out of trillions arriving at your eye every second. Every star is sending letters constantly. The mailbox is full beyond comprehension. Every glance at the sky is a glance at more mail than you can ever read. Some of it is from senders who are still alive. Some of it is not. You cannot tell the difference. Not from down here. Not yet. The library is real. The shelves are full. The lights in most of the building are off. The mail keeps arriving. The letters look identical, no matter who sent them. The senders may or may not still be home. That is the night sky. There is one more piece of this picture to lay in before we can talk honestly about Earth. We have looked at the dead worlds in our own solar system. We have looked at the kind of star most planets actually orbit. We have looked at the time delay in everything we see. We have not yet looked at the strangest thing about the only example of a living planet we have direct access to, which is that life on it has almost ended itself more than once. The biggest extinction in the history of Earth was not an asteroid. It was not a volcano. It was not a wandering star. It was the air you are breathing right now. That is where we have to look next. Part 7. The air in your lungs was once an extinction. The standard story about Earth is that we got lucky. The sun is calm. The orbit is stable. The moon has stabilized our axial tilt, so the seasons do not go wild over long time scales. The magnetic field holds. The atmosphere holds. The water holds. We had time. Life showed up. Life stuck around. And here we are, telling each other stories about how habitable our planet is, because we get to. That story is true in its broad outline. Earth is, by every measure we can apply, an unusually steady world. We have had 4 billion years of conditions that allowed life to keep going, in some form or another, without ever fully resetting. That is not nothing. That is the biggest thing. But it is also not the whole picture, because Earth has come very close to going dark more than once. The fossil record contains evidence of 5 major mass extinctions, plus a long list of smaller ones. These are events where so much of the world's biological diversity died off in a geologically short window of time that the fossil record itself becomes thin enough to fit in a much shorter section of any paleontology textbook. You can read the geological summary of a mass extinction in a single afternoon, even though the recovery from one took millions of years. There is a reason for that. There just is not much to say. The fossils stop. The pollen stops. The microfossils stop. The carbon ratios in the rocks change. The lights, for a moment, go out. The 5 major mass extinctions are the Ordovician Silurian, around 444 million years ago, where about 85% of marine species disappeared. The Late Devonian, around 372 million years ago, taking out something like 75% of species. The Permian Triassic, around 252 million years ago, which is the worst one we know about by far. The Triassic-Jurassic, about 201 million years ago, and the Cretaceous-Paleogene, 66 million years ago, which is the one with the asteroid and the dinosaurs that most people learned about in school. The Permian Triassic is the one that ought to make anyone uneasy. It is sometimes called the Great Dying because the numbers are so extreme. Roughly 96% of marine species died off in that event. Roughly 70% of terrestrial vertebrate species died off. Insects, which are notoriously hard to kill, had the only mass extinction event in their history during the Permian Triassic. The fossil record on either side of that boundary looks like 2 different planets. Almost nothing made it across. The trigger, by the best current understanding, was a massive series of volcanic eruptions in what is now Siberia, which pumped enormous quantities of dark side sulfur compounds acidified into the atmosphere, acidified the oceans, lowered ocean oxygen levels, and warmed the climate by something like 10 degrees Celsius in a relatively short window. It took the planet between 5 and 10 million years to fully recover ecological complexity after that. 5 to 10 million years where life on Earth was, in some genuine sense, on life support, hanging on, slowly rebuilding. That is the worst one we know about in the fossil record. But it is not the worst extinction event Earth has ever been through. The worst one happened so long ago that it almost does not have a fossil record at all. It had to single-celled organisms in shallow seas more than 2 billion years before any of the famous extinction events that have names you might recognize. It is called the Great Oxidation Event, and it is the strangest catastrophe in the planet's history because it was not caused by an asteroid, or a volcano, or a comet, or a wandering star. It was caused by life itself. Here is how it went. For about the first 2 billion years of life on Earth, the dominant organisms were anaerobic. They got their energy from chemistry that did not involve oxygen. There was not any free oxygen in the atmosphere to use. The early atmosphere of Earth was made mostly of nitrogen carbon dioxide, methane, water vapor, and a few trace gases. Oxygen was not on the list because oxygen is highly reactive and tends to bond with other elements, and there was not anything around to make new free oxygen in significant quantities. The bacteria and archaea that lived on the early Earth used chemistry that we would find profoundly strange today. They oxidized hydrogen, sulfur compounds, iron compounds, methane. They lived in deep ocean vents and in shallow tide pools and in stratified water columns. They were the entire biosphere for about 2 billion years. That was what life on Earth looked like. Then, a particular group of bacteria, the ancestors of what we now call cyanobacteria, evolved a new trick. They learned how to do photosynthesis using water as the electron donor. That sentence is technical, so let me say what it actually means. They figured out how to use sunlight, water, and carbon dioxide to build sugars, and as a byproduct of that chemistry, they released oxygen, free oxygen, pure oxygen gas, the first time it ever existed in significant quantities on this planet. It started slowly. The early oxygen-producing cyanobacteria pumped oxygen into the surrounding water, and the oxygen mostly got eaten up by chemical reactions with dissolved iron and other reduced compounds in the oceans. There was for a long time what geologists call an oxygens in sink. The free oxygen was being produced, but the oceans absorbed it almost as fast as it came out. There is evidence of this in the rock record. The banded iron formations, those layered red and dark sediments you can find in places like Western Australia and northern Canada, are the fossilized fingerprints of that process. Their alternating bands of iron oxide and silica were deposited as the dissolved iron in the early oceans precipitated out as it reacted with rising oxygen levels. Each band is a chapter in a story about life slowly poisoning the chemistry of its own oceans. Eventually the sinks filled up, the dissolved iron mostly precipitated out. The oxygen had nowhere left to go but up, so it started accumulating in the atmosphere. The atmospheric oxygen levels began to rise around 2.5 billion years ago. The rise started becoming significant. The Great Oxidation Event itself, the geological marker, gets dated to somewhere between 2.4 and 2.1 billion years ago, when the levels finally became high enough to leave a clear chemical signature in the rock record. For most of the life on Earth at the time, that was a catastrophe. Oxygen, for an organism that evolved without it, is a poison. It is a reactive molecule. It tears apart cellular chemistry. The anaerobic microbes that had spent 2 billion years building up the entire biosphere of Earth were not equipped to handle it. They could metabolize a lot of strange chemicals, but oxygen was not one they had any tolerance for. The rise of atmospheric oxygen, in geological terms a slow process, but in evolutionary terms a fast one, killed off something like 80 to 99% of life on Earth at the time. The number is hard to pin down because the fossil record at that age is thin, but the genomic and chemical evidence converges on it being a catastrophe of unprecedented scale. The first true mass extinction in the planet's histories was not caused by a rock from space. It was caused by life learning to do something it had never done before. The first mass extinction was the air we now require to breathe. I want to sit with that one for a second. Everything you have inhaled today is part of the same atmosphere that 2.5 billion years ago was a planetary disaster. The oxygen that you need to keep your brain working is the same molecule that exterminated most of the planet's biosphere the first time it showed up at high concentrations. It was a poison in its day. It became a fuel later, after enough organisms evolved to handle it. The reason multicellular life is possible at all is that oxygen is energetically rich, and animals like us have metabolisms that can extract a lot of usable energy from it. None of that would have happened without the Great Oxidation Event. None of it would have happened without life nearly killing itself. The recovery from that event took a very long time. Between the Great Oxidation Event and the appearance of the first complex multi-algae organisms in the fossil record, there is a stretch of about 1 billion years where the geological evidence is famously dull. It gets called, by paleontologists, the boring billion. There is not much going on in the rocks. Microbial life is around, it is quiet, it is catching its breath. The biosphere has been knocked back so hard that it spends 1 billion years just getting reorganized. Eventually, single-celled life learns to use oxygen efficiently. Eventually, eukaryotic cells appear with their internal organelles and complex chemistry. Eventually, multicellular life appears. Eventually, animals show up. But the time gap between the catastrophe and the recovery is enormous. The planet, in a real sense, almost stopped breathing 5 separate times in its history, and once the breathing itself was the thing that almost killed it. The atmosphere we now require to live is the same atmosphere that, when it first appeared, was an extinction event. That should change how you think about life on Earth. It changes how I think about it. The picture of Earth as a stable, life-friendly planet is true, but only in the broadest sense. Yes, the planet has supported life continuously for about 4 billion years. Yes, the conditions have stayed within a range that life, in various forms, could keep finding new niches inside. But within that broad continuity, there have been at least 5 major resets, plus the largest reset of all, the oxygen catastrophe. Almost everything alive has died, multiple times, in different ways, for different reasons. The thread of life on Earth is not a thick rope. It is a series of thin filaments, some of which broke, some of which survived, with the surviving filaments carrying everything forward each time. The relevance of all this to the question of life on other planets is straightforward and unsettling. If life on Earth, on the planet we are currently calling the success story, has almost been wiped out multiple times, and once was nearly wiped out by its own metabolic byproducts, what are the odds that life elsewhere has navigated similar transitions successfully? What are the odds that a young planet somewhere out there evolved photosynthesis in some form, and then choked on its own oxygen, and never recovered? What are the odds that a planet developed a powerful volcanic episode, or a glaciation event, or an atmospheric shift, and the recovery never happened? We have one example of life that survived its own evolution. The fact that we exist means it can happen. The fact that it almost did not, on the only example we have, means it might fail more often than it succeeds. That is a hard thing to know about your own planet. Earth nearly went silent. The fossil record gets thin enough in places to read in a single afternoon, all of which raises a different question. We have been talking about what happens to life once it gets going. We have not talked yet about how often life actually gets going in the first place. And it turns out that is a question we do not have a good answer for either. We have exactly one example. And one example does not tell you much about how common the thing actually is. That is where we have to look next, at the difference between a planet being habitable and a planet being inhabited, because those are not the same word. And the universe is, for all we can currently tell, full of planets that are one and not the other. Part 8. Habitable is not inhabited. There is a tendency when we talk about habitable planets to assume that habitabilities and inhabitation are the same word. They are not. They are not even close to the same word. Habitability is a description of conditions. Inhabitation is a description of what is actually living there. The first is a kind of resume. The second is whether anybody ever showed up to do the job. Here is what we actually know about life starting on a planet. We know it can happen. We know it because we are on a planet where it happened. That is one data point. That is the entire dataset. We do not know how often it happens on a planet where the conditions allow it. We do not know if it always happens, given enough time. We do not know if it usually fails. We do not know how to tell, from outside a planet, whether life ever appeared in it or not. We have hints, we do not have answers. What we do know is this. Earth had liquid surface water for somewhere between 0 and 700 million years before there is any clear evidence of life. That is the gap between the planet being habitable and the planet being inhabited on the only world we know that is both. Estimates of when Earth's oceans first stabilized as liquid water range from about 4.4 billion years ago, very early in the planet's history, to about 4 billion years ago, depending on which model you trust. Estimates of the earliest convincing evidence of biological activity range from about 4 billion years ago, in the most permissive readings, to about 3.5 billion years ago, in the more conservative ones. So, somewhere between 0 and 700 million years passed between Earth being capable of supporting life and Earth actually having life on it. That gap matters. It matters because we do not know what happened during it. Was life almost instantaneous? As soon as the conditions were right, with the apparent gap just being an artifact of an incomplete rock record? Or did it take 500 million years of chemistry running and rerunning before the first self-sustaining biological system finally took hold? The answer to that question would tell us, more than almost anything else, whether life is common in the universe or vanishingly rare. The trouble is, we do not know. The earliest fossils on Earth are debated. The earliest biosignatures, like the depleted carbon isotope ratios that biological metabolism tends to produce, are debated. The earliest microbial mats, called stromatolites, are debated. The earliest direct evidence of cells is debated. People publish papers refining these dates every year in both directions, and the field does not settle. The honest answer is that life on Earth got started somewhere between very quickly and very slowly, and we cannot tell which. What we can do is look at how complicated the first step actually is. The transition from non-living chemistry to a self-sustaining, self-replicating, evolving cell is a hard problem to define, let alone solve. It requires a particular kind of chemistry. You need information storage, like DNA or RNA or something equivalent. You need a way to translate that information into action, like proteins or their equivalents. You need a way to enclose the system, like a cell membrane. You need an energy source. You need a way to make copies that are imperfect enough that variation can accumulate, but accurate enough that the system does not fall apart. You need all of those things, in some form, working together on a planet where they have time to assemble. None of that is trivial. There are biochemists who think the assembly of the first cell from prebiotic chemistry is a problem so hard that it might happen only once in the lifetime of an entire galaxy by sheer statistical chance. There are biochemists who think it is so favorable that it should happen on any planet with the right chemistry within a few million years. Both groups are smart. Both groups are working on the same evidence. They disagree because the problem is genuinely hard and the available evidence is genuinely thin. A good way to think about this is the difference between dropping a seed on bare stone and dropping a seed in good soil. If you drop a seed on bare stone, you can be pretty sure nothing will come of it. The conditions are not right. The seed sits there, nothing happens. That is most of what we have found in the exoplanet catalogue. The conditions are wrong. Whatever happened to the seeds, they did not grow. But here is the part that takes a minute to absorb. Even if you drop a seed in good soil, you do not automatically get a tree. You might get a tree. You might get nothing. The seed might be the wrong species for the soil. The seed might be old. The seed might get eaten by a bird before it germinates. The soil might be good in all the ways you tested, but be subtly wrong in some way you did not think to check. Conditions in good soil are necessary, but they are not sufficient. The seed has to actually take. Habitability is the soil. Whether anything actually showed up to grow in that soil is a separate question, and it is not one we know the answer to in any general way. The universe is dropping seeds across hundreds of billions of planets. We do not know what fraction germinate. We have one example of a tree, and we have no idea whether the field is full of other trees we just cannot see, or whether the field is mostly empty soil with one tree standing in it. This is where the keyboard image returns. Earlier, I asked you to picture the habitable zone as a playable octave. The keys you can reach with one hand, the notes that work. The piano is sliding across the room. Mars's keys fell off the bench 3.5 billion years ago. Venus's keys fell off 700 million years ago. Earth's keys are sitting roughly in the middle of the playable octave right now. The keyboard image needed one more layer that I held back from earlier. Even when the keys are inside reach, somebody has to play them. The piano in an empty house is the same piano as the piano in a concert hall. The keys exist in both cases. The notes are physically possible in both cases. The difference is whether anyone is in the room to make sound. And from 100 light years away, with the best instruments we will ever build, the difference between an empty house and a full one is not always something you can hear. That is the question Mars sits at the center of. Mars had the keys for a long time, hundreds of millions of years, maybe close to 1 billion. The piano was inside the habitable octave. The air was thick enough. The water was liquid. The chemistry was sitting on the rocks, waiting to be played with. And we still do not know, from the rover deck, whether anything ever played them. The Sapphire Canyon sample is the best piece of evidence we have, and the people who wrote the paper about it are careful with their language because, even from one rock, they can tell. The question is harder than the headline. Mars is the most painful case to think about, because it sat there with everything it needed for a long stretch of time, and we still cannot tell. Mars had liquid water for hundreds of millions of years. It had an atmosphere. It had a magnetic field for a while. It had the chemistry. It had the energy sources in the form of volcanic activity and hydrothermal systems. By every measure we can apply from a distance, Mars was a planet that should have been able to support life in the same era when life was getting started on Earth. Did it? We do not know. We have a tube. We have a rock with patterns in it that on Earth would be a textbook microbial biosignature. We have the careful language of the people who publish the analysis, which is the language of suspicion rather than confirmation. We have, at the time of recording this, no way to bring that tube home, and the schedule for retrieving it has been stretched out into the late 2030s, possibly later. Even if we retrieve it, even if it comes back, even if the laboratory analysis confirms beyond reasonable doubt that the rock contains traces of biological activity from 3.5 billion years ago, that gives us a second example. 2 planets in one solar system where life appeared. From 2 examples, we still would not know the rate at which life appears in the universe in general. We would have a much better estimate. We would have made one of the most consequential discoveries in the history of our species. But we would still be talking about a single solar system with 2 examples in it, and a very long argument about how many there must be everywhere else. Venus is even worse. Venus may have had liquid oceans for 2 to 3 billion years. We can never check, in any meaningful sense, whether anything lived in those oceans. The surface of Venus today, with its acid clouds and lead melting temperatures and crushing pressure, is not a place that has preserved any biological record from the planet's habitable past. Whatever fossils Venus might have had, if it had any, have been baked, crushed, and chemically erased. Some of the most ambitious mission concepts for Venus involve atmospheric probes that could float in the upper cloud decks, where the temperatures and pressures are actually closer to Earth-like. There is even speculation about whether microbial life could survive in the cloud layer of Venus today, in the temperature zone about 50 kilometers above the surface, where the conditions are less extreme. But those are speculative searches. The historical record is gone. Then there are the worlds we have not even talked about. Europa, Jupiter's icy moon, with a subsurface ocean of liquid water beneath a frozen shell maybe 20 kilometers thick. Enceladus, one of Saturn's moons, which is shooting plumes of water vapor into space from cracks in its ice-covered surface, indicating an internal liquid water ocean. Titan, Saturn's largest moon, with a thick atmosphere and lakes of liquid methane on its surface, and the possibility of exotic chemistry that might be a different kind of life entirely. There are places, even in our own solar system, where the conditions exist for some kind of biology. We have barely begun to check. And then there are the exoplanets. 6,087 of them confirmed. Hundreds of billions estimated. Even with the most ambitious telescopes we can imagine building, we will almost certainly never directly sample any of them. The light from those planets, after it travels light years to reach us, can be analyzed for atmospheric composition. We can look for water vapor. We can look for oxygen, which on a rocky planet is a possible sign of photosynthesis. We can look for methane. We can look for combinations of gases that would not naturally coexist in equilibrium, which would suggest something is actively producing them. That is the toolkit we have. It is a powerful toolkit. But it is a toolkit for reading fingerprints in air. It is not a toolkit for sending a tube down to the surface and bringing it back. So even with the best instruments we will ever have, we may detect candidate biosignatures on dozens of exoplanets in the next few decades. We will probably never be able to confirm them by going there. We will be in the position we are in with Mars, but multiplied by hundreds. A rock we cannot reach, a signal we cannot follow up, a possibility we cannot close. The library is full of pianos. Some of them are in empty rooms. Some of them might not be. From outside the building, you cannot always tell, which means that when we look up at the sky and we try to figure out who is or is not out there, we have to be honest about what we are doing. We are not measuring presence. We are measuring possibility. The presence question, in many cases, will not be answerable in our lifetimes, in our children's lifetimes, in the lifetime of any institution that currently exists. The mailbox keeps filling, the letters keep coming. The senders keep being whoever they were when the light left them. And the one piece of the sky we can actually do something about, the only piece where we have any direct control, is the piece we are standing on. That is the part we have not really faced yet, because everything we have said about Mars, and about Venus, and about the kind of star most planets actually orbit, and about how easy it is for life to nearly poison itself, applies to Earth too. Earth is not the exception in the long arc of itself. Earth is on the same list. That is where we have to look last. Part 9. The window is open tonight. There is an instinct, when we talk about all of this, to position Earth as the exception, the one that worked, the lucky planet in the lucky orbit, around the lucky star, with the lucky moon, with the lucky magnetic field, with the lucky atmosphere, with the lucky biology. Everything broke our way. Everything held together. We get to sit here, 4 billion years into this, breathing the same air that almost destroyed the biosphere when it first appeared, looking up at planets that did not make it, and feeling on some level that we are not on the same list as them. We are on the same list as them. Earth is not the exception. Earth is the one in the middle. Earth is at the part of the story where the lights are still on, but the timer is running. The fact that we exist at this particular moment is not because Earth is a different kind of world than Mars or Venus. It is because we showed up at the right time. We are inside a window. The window is open right now. The window will close. Let me lay out the numbers. Because they are not abstract, they are specific. Earth formed about 4.5 billion years ago. Liquid water on the surface goes back at least 4 billion years, possibly 4.4 billion years. Life shows up in the rock record somewhere between 3.5 and 4 billion years ago. Complex multicellular life shows up around 600 million years ago. Animals with hard parts around 540 million years ago. The first land plants around 470 million years ago. The dinosaurs between 230 and 66 million years ago. Modern humans about 300,000 years ago. The agricultural revolution about 12,000 years ago. Modern industrial civilization about 200 years ago. That is the history. That is where we have been. Now look forward. The sun, as we talked about earlier, has been brightening at a rate of roughly 10% per billion years. The brightening continues. Multiple lines of evidence and modelling converge on a window of somewhere between 1 and 1.5 billion years from now, before the conditions on Earth become too hot for complex multicellular life to keep functioning. That does not mean the planet becomes uninhabitable instantly. It means the slow process of warming, evaporation, atmospheric loss, and oxygen decline crosses a threshold past which the kind of ecosystems we recognize cannot keep going. The oceans will be evaporating. The plants that need stable temperatures will struggle. The food chains that depend on those plants will struggle. The animals at the top of those food chains, including any version of us, will be in trouble. Microbes might hang on past that point. There are organisms on Earth right now that thrive in conditions that would kill almost everything else, in deep rock, in superheated water, in the chemistry of subsurface aquifers. Some of that life might continue to exist for hundreds of millions of years after the surface becomes uninhabitable for everything else. Earth's biological history might end with the same kind of organisms it started with. Microbes in the dark, carrying on in environments that no longer have a sky above them worth looking at. That is the first phase of the ending. Sometime between 1 and 1.5 billion years from now, the surface stops being a place for complex life. The atmosphere starts changing. The oceans begin to disappear. The same kinds of processes that played out on Venus begin to play out here. In about 3 to 4 billion years from now, the Earth's surface temperature is high enough that the oceans are essentially gone. The atmosphere is thinning. The carbon dioxide levels are climbing. The planet is, in slow motion, becoming a hotter, drier, more hostile version of what it used to be. Earth, by this point, would not look anything like the Earth we know. The continents would still be there. The mountains would still be there. The oceans would not. In about 5 billion years from now, the sun runs out of hydrogen in its core and begins its red giant phase. The sun's outer envelope expands. Mercury is swallowed. Venus is swallowed. By the most recent modelling, the central estimate is that Earth ends up inside the expanding sun. The likely engulfment timeline is somewhere around 7.5 billion years from now. So here is the full window. Earth has been habitable for approximately 4 billion years. Earth will be habitable for approximately 1 to 1.5 more billion years. The total window of habitability for this planet, from start to finish, is somewhere between 5 and 5.5 billion years. We are demonstrably past the middle. I want to say that one more time, because it is the part that is hard to hear and easy to skip over. Earth's total window of habitability is about 5 to 5.5 billion years long. We are currently somewhere around 4 billion years into that window. We have somewhere between 1 and 1.5 billion years left. The largest portion of Earth's life-bearing history is behind us, not ahead of us. That is not a doomsday claim. It is not next week. 1 billion years from now is so far in the future that the continents themselves will have rearranged into shapes nobody alive today would recognize. The species we are will not be here. The civilization we have will not be here. The Earth itself will only barely resemble the Earth we know. But the planet's own trajectory, the long arc of the planet itself, is past the middle. Earth is not in its morning. Earth is in its late afternoon. The evening has not started yet. But it will. The window is open. The window will not be open forever. Mars showed us what comes after. Venus showed us what comes after. A different version of after. Earth is showing us what during looks like. The during is the whole point. The during is what makes the universe interesting when it happens. The during is rare, by our best guess, both in space and in time. The way I have come to think about all of this is as a long evening. The day is over. The evening is here. The light is still warm. The window is still open. The night is coming. But the night is not here. We get to sit on the porch of this planet, while it is still possible to sit on the porch of this planet and watch the sky and read the letters and try to figure out who else, somewhere out there, might also be sitting on a porch while their light is still warm. The window will not stay open. That is true. It is also true that the window is open now. Both things are true at the same time. The thing about a window being open is that what matters is whether it is open in the moment you are standing in. Earth's window is open. The oceans are still liquid. The air is still breathable. The magnetic field is still up. The geological clock that keeps the carbon cycle balanced is still running. The species are still adapting. The seasons are still turning. The thing that planets only get to do for a sliver of their lives, the thing called supporting life, is something this planet is currently doing. You are an example of that. You are listening to this, or drifting towards sleep with this in the background, because Earth is, at this moment, allowing it. Somewhere on a world we have not found yet, the same conditions may be true tonight, and someone on that world might be looking back at a sky that includes our sun, wondering the same thing you are wondering. Maybe they are putting it into words in a language that has nothing in common with ours. Maybe they are not using words at all. Maybe they just have an internal sense, in whatever counts for them as awareness, that the night is large, and that they are a small part of it, and that something might be looking back. Or maybe they are not. Maybe their lights went out a long time ago, and we have not noticed yet. Maybe the light we would need to see them is still its way to us, taking centuries to make the trip. Maybe by the time we get the message, the senders will not exist anymore. Maybe nobody is out there at all. Maybe Earth really is the only place where the chemistry came together. That last one is a possibility you can also sit with. It does not have to be the most likely answer. It just has to be allowed. The fact that we do not know is the actual situation. Not knowing is not a problem to solve tonight. It is a place to sit, for now, until more information comes in. The universe is patient. We have less time than it does, but we have enough time for tonight. Either way, the porch light is still on here. The sky is still up there. The numbers still work. The water is still liquid. The lungs still breathe. The rocks under your feet are still old enough to remember things you cannot imagine, and stable enough to keep doing the slow work of holding the planet together for another billion years, give or take. Mars's porch light is still on, in the technical sense that the sun still shines on Mars, even though the house is empty. Venus's porch light is still on too, in its own way, behind sulfuric clouds, on a planet that is glowing hot under a sky that is heavy and dim. TRAPPIST-1 is still flaring 6 times a day. The library is still standing, with its lights mostly out, and its shelves still full. The mailbox is still receiving. And here, tonight, you are inside a moment that most planets never get to have at all. You do not have to do anything with that. You do not have to feel awe, or sadness, or anything in particular. You can just notice it. The window is open. You are in the room. The light is warm. The night will end the way nights end. The morning, if there is a morning where you are, will come. The seasons will keep turning. The earth will keep doing what it has been doing for 4 billion years, for as long as it can. The third door is the one we walked through tonight, not teeming, not empty, full of finished, full of windows that were open once and closed, full of porch lights still on with nobody inside, full of letters arriving from senders who may or may not still be home with envelopes that all look the same, full of pianos in empty rooms with the keys still inside the playable octave and nobody to play them. That picture does not make us less rare. If anything, it makes us more so. Not because nothing else made it, because something else once did, somewhere, and stopped. And we are still here for now. The porch light is still on here. The rock is still on Mars. The tube is still sealed. The wind is still blowing red dust across it. The Milky Way's library is still standing in its quiet way with most of its lights out and its shelves still full. And you tonight are inside the open window. That is enough. Sleep well.